My name is Cristiana and I work at Minas. I will present the paper Performance Evaluation of an Indirect Solar Dryer for Corn Drying. The authors are Gisele, Silva, André, Ferreira, Rogério, Coutinho, and me, Cristiana, Maia. We are from Cefet, Minas, in Minas. Inadequate preservation techniques and poor storage methods lead to deterioration in the quality of agricultural products. Drying is a process used to increase the quality of the products and to preserve them with reduced risk of deterioration. Open sun drying is a technique where the products are directly exposed to the sun. It has a lot of disadvantages, as the products are subjected to environmental conditions and to little animals. In dryers, it's possible to protect the products against the animals and rain. Solar dryers use only a renewable and cheap energy source, but the drying is still controlled by fluctuations of solar radiation and ambient temperature. Hybrid dryers use an auxiliary source of energy to complement the solar energy when it's not enough. The objectives of the paper are to evaluate a sustainable indirect hybrid solar electric dryer used for drying corn kernels, and to compare the results with open sun drying. The system consists of three main parts: the PV system, the solar collector, and the drying chamber. Here is a picture of the system, and in which we can see that it has 4.9 meters of length and approximately 1 meter of width. The solar dryer consists of the solar collector and the drying chamber. In the solar collector, the airflow is heated. The products are placed in trays inside the drying chamber. The PV system consists of a photovoltaic module, batteries, and a charge controller used to feed the fans, and an electrical heater. The solar collector has a slope of 20 degrees, equal to the latitude of Belo Horizonte, city in which the dryer is located. The flow is forced by the fans and passes through a duct below the PV module. The heat dissipated by the PV module surface preheats the drying airflow. The airflow is heated by the solar collector surface and enters the drying chamber. Since its temperature is higher than the temperature of the products, its relative humidity is lower and it removes humidity from the products. The power generated by the PV is used to feed the fans, and the remaining is stored in the batteries. When the solar radiation is not enough to raise the airflow temperature above ambient temperature, an electrical heater is used. It's important to highlight that the electrical heater is fed by the PV system, which ensures sustainable characteristics to the dryer, making it possible to use it in locations where there is no access to electricity. The measured variables were solar radiation, air temperature, the surface temperatures, the relative humidity of the air, and the moisture content of the products. The tests were performed from 7:30 a.m. to 5:30 p.m. The initial moisture content of the product was determined putting the products in a drying oven at 105 degrees Celsius for 24 hours. and measuring the mass of the product after and before it was put in the oven. The tests were performed on September 27th, corresponding to the beginning of the spring season. Here we can see the measurement sensors and where they are placed. The relative humidity of the air was measured at the inlet and the outlet, points 1 and 8. The airflow velocity was determined at the inlet, point 2, using an anemometer. The solar radiation was measured with a pyranometer placed in the plane of the collector, here in point 7, and the temperature was measured in several positions. Here at the inlet, one of the sensors is also a thermohygrometer anemometer. It was measured the temperature of the surface of the PV module and the solar collector, the temperature of the air at the inlet of the solar collector, inlet of the drying chamber, and at the outlet of the system. Mathematical model includes the drying efficiency. It's defined as the ratio of the energy used to evaporate the product moisture and the energy supplied to the control volume. The moisture content of the corn was measured inside the, putting the product inside the oven. So, this is the moisture content, and MSP represents the mass of the sample, initial and final. The instantaneous moisture content of the sample is defined by Wx, and it's calculated based on the instantaneous X, initial mass of the products, and the moisture content of the corn. We also compared the performance of the solar dryer to open sun drying, comparing the times required to achieve the final moisture content. T is the time required. Here we can see in the results part the main parameters of the problem, the test. Here we can see the initial and final product mass, the initial and final moisture content of the product placed inside the dryer, the average drying time until 13% of moisture content is achieved, the average solar radiation, the average ambient temperature, the average drying chamber temperature, the relative humidity, and the average drying efficiency. This graph represents solar radiation and ambient temperature during the tests. We can see that it was a sunny day with clouds appearing at 1:30 p.m. only. The solar radiation increases until a maximum is reached close to noon and then decreases. The ambient temperature was always high, ranging from 23 to 35 degrees Celsius. And the average temperature was 30 degrees Celsius. The solar radiation, the average value was 652 watts per square meter, and the maximum was 990 watts per square meter. This figure represents the drying curve. We can see the results are compared for natural open sun drying and solar drying, which represents the drying curve of the products placed inside the dryer. We can see that solar dryer achieved the final desired moisture content of 13.5% in approximately 7 hours, and the open sun drying failed to achieve this value in 24 hours. We can see that the measurement points were from 7:30 to 5:30 p.m. And then the next day we measured the values again. So that's this point, 24 hours, representing 7:30 of the next day. The final moisture content was 12.8 for the solar dryer and 15.8 to natural sun drying, which means that open sun drying was not able to dry the products until the desired moisture content. Both had the same initial moisture content. In this figure, we can see the temperature of the airflow and ambient temperature. We can see that the airflow temperature varies according to solar irradiation, which means that it increases during the day until a maximum close to none and then decreases. And at 1:30 p.m. there was a decrease as a consequence of the clouds. We can also see that the airflow reached temperatures above close to 70 degrees, which is a high value. And we know that the maximum temperature of the corn is close to 90 degrees, and this value was not reached inside our dryer. As conclusions, the greater the drying temperature, the greater the air's ability to remove water from the product. As the product dries, less humidity is available to be removed, making it more difficult to dry the products, which leads to the second conclusion. At the beginning of the drying process, when there is more humidity to be removed, the moisture content is high, and also the drying efficiency. As a result, we could see that the drying efficiency of the dryer was 6.1%, and the duration of natural open sun dryer was approximately 44% higher than the drying inside the dryer, for a final product moisture of 15.8%. We would like to thank Cefet MG, PUC Minas, and the agencies CAPES, FAPEMIG, and CNPq. Thank you. And if you need to contact me, there are my email, my webpage, my lattice, and my YouTube channel. Thank you very much.